Ever feel like you need to quickly grasp something complex? Well, today we're taking a deep dive into something pretty amazing,
Yeah.
how researchers are teaching computers to recognize and identify different speakers in audio.
Yeah.
It's a technology that's becoming increasingly important. I mean, you see it popping up everywhere,
Absolutely.
from, making meeting notes more efficient to even improving accessibility for podcasts.
It's really interesting because we're moving beyond just transcribing the words that are being said, and now we're also trying to understand who's saying what.
Right.
And that unlocks a whole new level of insight into any audio recording.
For sure. So to kick things off, let's make sure we're all on the same page with some basic terms.
Okay.
When we talk about speaker recognition, we're talking about verifying whether a specific voice belongs to a particular person.
Hmm.
Then there's speaker identification, which is all about figuring out which person from a group is speaking.
Right.
And lastly, we have speaker diarization, which is the process of determining who spoke when. So in this deep dive, we'll explore the techniques that make all of this possible.
At the heart of all this is the fact that every voice has unique characteristics, kind of like a vocal fingerprint.
Right.
Speaker recognition uses these distinct features, like the way someone speaks, the pauses they take, and the acoustic patterns to identify or verify them.
So it's not about the words themselves, but more about how they say them.
Exactly. It's all about the nuances of their voice.
Okay, so how did these systems actually go about analyzing those unique vocal fingerprints?
Well, they use a technique called feature extraction, which is like isolating the most important elements of a voice.
Ah.
One common method is using something called MEL frequency substral coefficients, or MFCCs for short.
MFCCs.
Yes, these give a condensed representation of the sound frequencies that make up someone's voice.
Okay.
But even more advanced than that, we now have speaker embeddings. These are like digital snapshots of a voice created using machine learning.
Interesting. So are these embeddings more accurate?
Oh, they've significantly improved the accuracy. Early methods were a bit like trying to recognize a song based only on its main melody.
Okay.
But with embeddings, we're able to analyze all the harmonies and subtle instrumental nuances that truly make a song unique.
That makes a lot of sense. So are there different types of speaker recognition systems, or do they all kind of work the same way?
There are actually different ways these systems are applied. We have what are called text-dependent systems, where the speaker has to say a specific phrase or word. This can be very accurate for things like voice passwords.
Okay.
But then there are text-independent systems that can work with any speech.
Sure.
These are much more versatile for things like transcribing natural conversations.
Gotcha. So we've talked about recognizing a single voice, but how do these systems deal with multiple speakers? Like figuring out who's talking in a group and when?
That's where speaker identification and diarization come into play. Speaker identification often relies on a database of pre-recorded voice prints. So when a new voice speaks, the system generates a voice print for that voice, often using neural networks.
Right.
Then it compares that new voice print to the ones in the database to find a match. A great example of this is call centers identifying returning customers.
So it's like a matching game with voice prints.
Exactly.
And diarization, that's all about sorting out the who said what, when, right?
Precisely.
Yeah.
It's a multi-step process. First, we use something called voice activity detection, or VAD,
Okay.
and this filters out any silence in the audio. Then comes speaker segmentation, which divides the audio based on changes in the speaker's voice.
So kind of like chopping up the audio into different speaker segments.
Right, and after that, we use speaker clustering algorithms.
Wow.
These group together segments that are likely from the same speaker and assign generic labels like speaker 1, speaker 2, and so on.
Gotcha. So what are some of the techniques used to actually tell different speakers apart?
Well, we have various clustering algorithms like k-means and agglomerative hierarchical clustering, or AHC.
Right.
These algorithms have been around for a while, but now deep learning models are playing a huge role. They can learn to pick up on very subtle differences in voices. And then there are end-to-end neural diarization, or END models.
END.
Yeah. These models can directly output who is speaking and when without the need for separate steps.
Wow. So this is all super complex. Are there different levels of difficulty depending on the audio setup?
Absolutely. When you have multi-channel audio, meaning there are separate microphones for each speaker,
Okay.
it's relatively simpler to separate the voices. But when it's single-channel audio, where everyone's speaking into the same microphone,
Right.
it becomes much more challenging because of overlapping speech and background noise.
That makes sense.
But researchers are actively working on addressing these challenges using advanced AI techniques.
All of this is fascinating. It seems like this technology is being integrated into more and more everyday tools and services.
Oh, absolutely.
What about live transcriptions? Like, how does this all work in real time?
That's a great question. Live transcription services need to be able to process audio in real time, so they require low latency and what's called online diarization.
Okay.
So several platforms like Stream, Agora, Speechly, Symbol.ai, and Oracle Cloud are incorporating these capabilities.
So for developers who want to play around with this tech themselves, are there open source options available?
Definitely. There are some fantastic open source tools and libraries out there. For instance, Pano.audio, which uses PyTorch, is really great for end-to-end diarization.
Okay.
SpeechBrain is another one that provides very robust diarization tools. And then you have NVIDIA Nemo, which is a very powerful and modular framework.
So there's a lot to choose from.
Yeah, there's something for everyone.
Even well-established tools like Caldi have diarization capabilities these days. And you even have efficient alternatives to Whisper, like Faster Whisper and WhisperX, which include diarization features.
It's great to see the variety out there.
Definitely. So looking ahead, what are some of the biggest challenges in making this technology even better?
One of the key challenges is finding the right balance between speed, accuracy, and computational resources, especially in real-time applications.
Right.
And then there's the natural variability in how we speak. Different accents, emotions, background noise, all of that adds complexity. And of course, there's the issue of overlapping speech, which is really hard to disentangle.
So it's not just about the algorithms, but also about how we handle the messy realities of human speech.
Exactly. It's a combination of both.
So how do we even measure how well these systems are performing? Are there standard metrics?
There are. Some key metrics include diarization error rate, or DER, which tells us the percentage of speech that's incorrectly labeled.
Okay.
We also use Jacquard error rate, or JER, and word error rate, or WER, which are both relevant in evaluating the accuracy of the transcription.
So where are we seeing all of this being applied in the real world?
Oh, it's popping up everywhere. You have Python libraries like Assembly AI that make it easy to incorporate speaker diarization into your projects.
Right.
We also see it in web applications that use WebRTC and WebSockets for real-time communication. And of course, in backend frameworks like Flask and Django.
Interesting.
And even in game development with Unity, you can use native features, asset store options, or cloud service SDKs like AWS Transcribe Azure and Google Cloud to implement speaker diarization.
It's amazing to see how widely applicable this technology is.
Absolutely. And the applications are only going to grow from here.
This has been a fascinating look at how we're teaching machines to understand the nuances of human speech.
Yeah, it's really exciting to see how far we've come.
What's particularly exciting is to think about where all of this is headed.
Right.
I mean, we might even see large language models playing a bigger role in refining these systems in the future.
Absolutely. The possibilities are endless.
So now that you know more about how these systems work, I'm curious what potential applications are sparking your interest. What new possibilities are you considering?
I'm eager to hear what you come up with.